So now we're going to talk about this concept called rational functions, okay? And rational functions are basically functions of the form p of x over q of x, where q of x is not equal to 0, okay? So now let's consider what happens with a function that looks like this. So with the function f of x is equal to 2 over x minus 1, here's what you know. As x goes to, well, infinity, this function f of x goes to 0. So all you're doing is you punch in numbers like really large onto your calculator, and you'll find that if I put x is like 1,000,000, the entire thing vanishes. It almost goes to 0 as time goes on. As x goes to negative infinity, guess what? As x goes to negative infinity, the same thing happens. F of x goes to 0 again. But in essence, this is going to be 0 from the negative half of the x-axis. From the other one, it was from the top half of the x-axis. So here's the next part. So what about when you look at the equation? Remember what I told you? The original equation couldn't have x equal to 0. So here's what we look at. So as x goes to 1 from the negative side, right? So imagine you take a number like 0.99 or 0.99999, right? Here's what happens. Fx ends up blowing up towards negative infinity. So if you punch in that 0.99, it's going to be a negative number, which means you're going to have 1 divided by 0.001, which means this blows up to a very big positive number. Or, sorry, negative number. So now, as we have x approaching, say, 1 from positive number, from the bigger side of it, we find that f of x goes to positive infinity. So it just increases. So if I had chosen 1.01, that's what's happening. So just to give you an idea and some clarification of what all this means, this is what I'm saying. For when I'm actually talking about this plus sign, this is actually telling me as x approaches from the right, basically, we're saying that our x value, our original function changes in some way. All right. Now, this part here is actually saying as x approaches, right? That's what it means. Okay. So there's not much else to say there. All right. So now let's move on to our problems of actually graphing this thing, because every time we do these things, we're always graphing. So what I'm going to do is I'm going to shrink this entire problem here, and I'm going to make sure that we can see the basics of all the information that we've gathered, right? Now, here's what I want you to understand. When you're actually looking at this thing called x is equal to 1, x is not equal to 1, this is called a vertical asymptote. Uh-oh. Spelled that wrong, didn't I? Asymptote, right? Now, a vertical asymptote literally looks something like this. You've got your line, and you find x is equal to 1, and then all you're doing is just drawing a dashed line to represent that this is a set that the graph cannot touch. So now the asymptotes are lines that the curve approaches, right? There's three types that we have. The first type is called the vertical asymptote that we're looking at, okay? All right. There is a second one called a horizontal and a slant. So we're going to talk about the vertical right now, and then we'll kind of put it all together later. So right now we have a vertical asymptote, right? And based on what we talked about earlier, as x goes to, ready, positive infinity, our graph is above the x-axis. It is above the x-axis. So what happens is, as it goes towards infinity, the graph kind of does this. Zooms down, but never actually touches the x-axis, right? Now, on this other side, where x is going towards negative infinity, our graph is actually doing the same thing, but instead of approaching from the top, it's approaching from the bottom of the graph, okay? So that's what we got so far, right? Now, let's go and talk about some other stuff, right? Maybe we want to know like some extra points and stuff like that. If we let's go and find the y-intercept. Sorry, the y-intercept. So if I wanted the y-intercept, right, you'd go y is equal to, well, 2 over, we'd let x equal 0, subtract 1, so that means x is, so y is negative 2. So at negative 2, we know that our graph crosses the x-axis, so this is 1. So we know that our graph approaches infinity, approaches the graph towards 0, going towards negative infinity, but when it's coming this way, towards this graph, towards this thing, right? We said that if x was less than 0, it went and blew up towards negative infinity. So our graph actually does that. Now, the same can be said about this one. If we do it, we also said that as x approached 1 from bigger numbers than 1, like really, really tiny numbers, like 1.0001, our numbers just blew up, right? So our graph kind of looks like this. Now, I didn't draw it real nice, but I'll show you what the graph should really look like. The graph literally looks like this. It has to be kind of symmetrical, and it zooms out, and it does this and this, but it always goes towards 0, and we have our vertical asymptote. But if you take a look here, you'll notice that the graph doesn't cross the x-axis here, right? So it actually approaches 0 from the underside and then approaches 0 from the top side here, right? But never actually crosses. This is the second type of asymptote that we have. We call this a horizontal asymptote. Asymptote. Let's go and correct this one here. Asymptote up here is not spelled with 2 S's. Mind you, they are a really annoying thing to work with if you don't know what you're doing. So asymptote is just 1 S. 1 S. And remember, this part here was called a vertical asymptote. And this was the vertical asymptote where x is equal to 1. Okay? Where x is equal to 1, the graph does not cross either the horizontal or the vertical asymptote. Okay? So now let's go talk about vertical asymptotes, just to make sure we understand what that means. So now we're going to talk quickly about vertical asymptotes. So vertical asymptotes are these type of graphs that you see here, right? So what I'm going to do is we're going to zoom in and we're going to actually talk about them. So for this first graph on the left, we'd say as x goes to the value of a, so this value here where our vertical asymptote is, where x is equal to a, is it's being approached from the negative side, so from the smaller end. That means f of x is blowing up to positive infinity. For this next one, for this second graph here, for the second graph, we can say the following. We say as x approaches a from positive side, so from the bigger side, so that's what the plus means. We say f of x goes to, so here's what's happening. We're zooming in, zooming in, zooming in. We're moving in, moving in, and moving in. And instead of crossing x, it blows down towards negative infinity. So we're going to say it goes towards negative infinity. So that's what we're saying as we're approaching those lines. So for x is equal to a, for this problem, for this third one, we have a dilemma. We have two different possibilities. So as x approaches a from the negative side, so that's this thing here. So as it approaches from this side and comes closer and closer and closer, our f of x blows up to positive infinity. So we start here and we notice our y gets closer and closer, but never actually touches. And so we say, as x approaches from a from negative numbers, f of x will approach positive infinity. So it's just blowing up. So the other side is as x approaches a from the positive side. So that's what the plus side means, right? F of x goes towards negative infinity. So there it is. Those are basically the things we say for those graphs. So when you see a graph that does something like this, you know that is what your graph is doing. So let's go and take a look at another graph, right? Another cool graph. So let me just move all this stuff up and we will, we'll move all this stuff up and we'll see what we've got here. So this is our next example for our vertical parabolas. You could have a parabola that looks like this, or not a parabola. You could have a graph that looks like this. So let's say I have x is equal to a here. So we've got a dashed line. So we've got a dashed line where x is equal to a. So this is x is equal to a here, right? Now imagine if I had two lines that did this, that came in from the left and blew straight up, and came in from the right and blew straight up. So I mean left and right. So coming from the left blows up, coming from the right and blows up. So here's what you would say, mathematically speaking, based on what's going on. You would say, as x approaches a from the positive side, you'd say f at x approaches positive infinity. And then when you're looking at as x coming from the negative side, the smaller side, the left side of our graph, i.e. this part, our y values blow up to positive infinity. All right, you'll notice how I always say positive or negative infinity. That always gives me the chance to basically acknowledge that I'm either going up or down with respect to y. Okay, and that's what we have. So you could also say this in order, if both of them are both approaching, if both from the left and the right, they're both approaching positive infinity, you could say to save yourself some time, as x approaches a, f of x is going to approach just positive infinity. And you're done. So you could save time if both sides are going towards positive infinity. You could say it that way. All right. Here's one note that I want you to remember. Note, with a vertical asymptote, the graph never crosses. Let's say, let's use crosses the VA. Remember, vertical asymptote, ever. That's what you need to remember. All right. All right. Here is the new concept that we're going to take a look at. It's called the horizontal asymptotes. The key idea here is that your graphs could have a horizontal asymptote running across it. So think of it as a dashed line. And I'm going to call this y is equal to c. And what could happen is my graph could come down, come up, and then follow that line. Okay? So you would say the function can cross these vertical asymptotes. So here's another graph. You could have a horizontal asymptote doing this. We still have y is equal to c. But maybe it comes down from the left, it comes down and goes towards the left, but never crosses this y asymptote, right? We can also have a graph that looks like this. We have our horizontal asymptote at y is equal to c. And instead of that, we've got something going on like this. All right, so let's go and say what these mean as x goes to infinity and negative infinity with respect to these asymptotes. All right, so for the first graph, what you're going to say is the following. So you want to look at what's actually trending in the problem. So you'll notice that you don't care about this, but you do care about what's happening with this side of the line because it looks like it's going closer to the line but never crossing it. So you would say as x goes to infinity, you'd say f of x goes to that c value that we were looking at. That's it. That's how you'd know that you got a horizontal asymptotes, right? Now, the second typical asymptote that we have here looks like this. So remember, it comes down and goes across, right? And because it comes down, it goes across. Because this one comes down and goes across, you could say as x goes to negative infinity, f of x goes to the value c. So, but you know, it can cross, right? It's the same thing, okay? So you got to remember, for these horizontal asymptotes, you can cross them. Okay, so now for the last one. For the last typical graph that you would see for horizontal asymptotes. So they're both approaching. So for this one here, you could say, well, as x approaches positive infinity, you know that f of x goes to c. As x goes to negative infinity, f of x still goes to c because it goes closer and closer to that line, right? And we're done. Okay. So now this is the last typical one that I want you to know. Okay, this is the last typical one. So those were the three that we had. So let's go over them one last time. Just take a look. So those were the three that we had. Now the last graph that you'll see is something that looks like this for our problems today. So you might have one where you have your horizontal line, your y is equal to c, but what happens is our graph has another horizontal asymptote, a second one. So this is y is equal to, say, k. So for this top one, imagine if I had a graph that looked like this and went like that, right? So for one side, you would say as x goes to positive infinity, f of x goes to c. For as x goes to negative infinity, so that's us traveling this way, it eventually turns into k. So you'd say f of x turns into k, or looks like k in the end. So now let's go and do some examples where we're taking a look at how to find the vertical asymptotes. So here's our first problem. We're going to find the vertical and horizontal asymptotes of this equation here. Fx is equal to 2x plus 1 over x squared minus 4. Okay, so this is how you do the horizontal asymptote. So start with your basic function, x squared, or f of x is equal to 2x plus 1 over x plus 4. Now, here's the thing. As we have x approaching infinity, this function turns into 2x over x squared. Just think of it this way. The 1 and the 4 disappear. Doesn't matter. Which simplifies to 2 over x, right? Which, if x keeps blowing up and getting bigger, like 2 over a billion, this essentially turns to 0. So y is equal to 0 is the horizontal asymptote. That's how you go and do your horizontal asymptotes. It's all about taking a look at the limits and how those things change. Now remember, when you start with your original equation, right, and you're going to do the limits, you drop all the constant values and then simplify and then see what happens when x goes to positive or negative infinity. So now let's talk about this thing called the vertical asymptotes. For the vertical asymptotes, this is what you have to do. So let's just call that the VA to save time when we're writing. So for the VA, here's what you have to do. You have to find where the denominator is equal to 0. So you look at the original denominator and you got x squared minus 4. Set that equal to 0. You factor, you got x minus 2 and x plus 2 is equal to 0. So here's what it tells us. X cannot equal the following, 2 and negative 2. And that means these are your horizontal asymptotes. That's it. We're done. Sorry, you're not your horizontal asymptotes. You're vertical asymptotes. All right, so those are your vertical asymptotes. X is equal to 2 and x is equal to negative 2. We're done. Now, the next type of vertical asymptote is called the hole. Okay, so this is the situation where you have a hole, okay? So you start off with f of x is equal to x squared minus 4 over x minus 2. So here's how we do this. The solution is we say, well, x cannot equal 2 based off the fact, so this is our vertical asymptote. You think it's a vertical asymptote, but here's what happens. If you factor the top, you get x minus 2 and x plus 2. Right? Remember how we said that x cannot equal to 2? So by saying that, you can cancel out these parts. So the original graph looks like x plus 2. So fx looks like x plus 2, but x cannot equal to 2 from before. So what that means is we literally have a graph of x plus 2 that looks like this. And then at x equals 2, we go have a hole. So we're going to have a hole. It's hilarious. So instead of drawing a vertical asymptote, you just got a hole that represents where we cannot go through. Now, for the horizontal asymptote, let's go and take a look at that. So before we do that, you're just going to say there is a hole at x equals 2, but our graph looks like f of x plus 2. So now imagine we're going to take this problem here, and we're going to go and find the horizontal asymptote. So here's how we find the horizontal asymptote for the function f of x is equal to x squared minus 4 over x minus 2. So to find it, you literally say, okay, as x goes to infinity, you have to think about what it looks like. This turns into just x squared over x, doesn't it? Right? So x squared over x changes to x, doesn't it? So, geez, there's no horizontal asymptote. No horizontal asymptote. That's all it is. There's no horizontal asymptote in that case. So there is no HA for our problem. But later on we'll find out that this could be a slant asymptote. So just make sure that you highlight this information, and then we'll move on. For the last part of this lesson, I'm putting up a sample note for the last example in this problem, okay? And this sample is, I call this example D, and this is for this problem. F of x is equal to x over 1 minus x squared, right? There are a few things that you're going to do. You're going to do your graphical analysis where you figure out your symmetry, you figure out your intercepts, you figure out your vertical asymptotes, you figure out your horizontal asymptotes, and find some additional points. Once you've done that, you're going to be able to graph it. Now, you're going to see that work, and it's going to be posted online. I want you to work on these problems. Page 170, and you're going to do number 9, 11, 15, and 17. And I will post that in the next few minutes.